Hello, I'm Golda.
I'm Serena.
And I'm Connor.
We're part of Cooper Union Summer STEM program, of course, and our division's called iGEM, and our goal was to look for problems and find solutions using genetic engineering.
So what is a biosensor? A biosensor is a system that uses a biological component or part, such as a bacteria, to sense a material or toxin in the air, such as arsenic, lead, or even nicotine. Some examples of common biosensors present in our everyday lives are both pregnancy tests and glucose tests that diabetics use. Pregnancy tests use the bacteria that detects a pregnancy hormone, HCG, which then shows present as a pink line indicated by the bacteria. Glucose tests also use biosensors to measure the amount of sugar in the blood.
So in order to create a biosensor, you need to create a circuit, and a genetic circuit, and that requires 4 parts. The first part is a promoter, and that makes the RNA polymerase begin transcription, so the DNA turns into mRNA. Then you have the ribosomal bonding site, short with RBS, is short for the ribosomal bonding site, and that is when the mRNA binds to the protein. Then comes open reading frame, or the protein, and that has the codons that encode for said protein. A general sequence ends with a terminator that stops transcription. But in order to make a circuit, you need to have antibacterial resistance, because something else other than your sequence may grow in a culture, and we want to get rid of that and just be left with our circuit. So antibacterial resistance usually contains ampicillin, and anything that doesn't have that resistance that the gene has is killed off.
So this is an example of a complex circuit regulatory gene. So many complex circuits have a component that's called a regulatory gene. And what regulatory genes do is they create a repressor, shown by the green box. And repressors bind to the promoter or operator region, shown by the red box. This disables transcription, and so the gene you're trying to express can't be expressed. When an inducer, such as lead or anything you want, is present in the system, it will bind to the repressor, making it then unable to bind to the promoter, which will then allow transcription to occur and your gene of interest to be expressed.
Once we've created the gene, we use polymerase chain reaction, or PCR, in order to amplify the amount of DNA that we have. In order to do this, we heat up the DNA, which allows it to denature. From there, we anneal primers onto the end of the DNA, and polymerase then transcribes the DNA to create further copies. We do this about 20 to 30 times, which will create about 1 million copies of the DNA, which we then can use to insert into the bacteria. So once we've amplified our gene of interest, we insert the gene into a plasmid, and the plasmid that we used for our experiment was PUC19. In order to insert this gene into the plasmid, we use restriction enzymes or molecular scissors to cut the plasmid. From there, we then ligate the gene onto the plasmid, and we then insert the plasmid into DH5 alpha E. coli.
So in iGEM, we were divided into 4 teams, A, T, C, and G. We created biosensors, and the 4 biosensors we created detect lead, nicotine, arsenic, and potassium. We hope you enjoy the rest of our presentations, and all questions will be answered at the end. Thank you.
Hi, we're Team G, and we're here to present our lead biosensor.
The name of our biosensor is Let It Out.
We're really excited to present to you. I'm Nadia Umlauf.
I'm Serena Madelon.
I'm Serena Iman. And I'm Mackenzie Morrison.
Okay, so the inspiration for our biosensor was Flint, Michigan. In early of 2014, the residents of Flint were hard-pressed to find a clean source of water after their city had changed their water source to the local Flint River. And the water from the Flint River basically corroded the old lead piping that brought water to the town. And as a result, this caused lead contamination in the water, and this lead contamination led to lead poisoning and is also thought to be the cause of a bunch of outbreaks for different diseases such as Legionnaires. So our biosensor would let people privately test water in their homes, and there are private testers on the market currently, but they're usually very inaccurate and they require meticulous work, so a lot can go wrong. This leaves the people who want to test their water in their homes with only one other option, and that's to collect a sample of their water and send it to a lab, but that takes both time and money. So our biosensor would be an easy fix for this problem. So what does our biosensor do? Basically, our biosensor detects lead contamination in water, and so our biosensor will release a green fluorescence every time it senses lead in the water. So the amount of lead fluorescence correlates to the amount of lead in the water. So the more lead there is, the more fluorescence you'll see. And this fluorescence is best seen under a black light, but can also be seen under plain light as well. And it'll look something like this.
So there were three main parts to our linear biosensor: the PBR operator and promoter region, the PBRR, which was our regulatory gene, and GFP, which was what provided our green fluorescence. Both PBRR and the promoter and operator came from bacteria Ralstonia malodorans, and inside this bacteria, it functioned as both a filtration and a detection system for lead, so we adapted these genes out of that. So how does it work? This is another diagram depicting a regulatory gene. The repressor that is created by our PBRR is binded to the promoter, not allowing transcription to occur. When lead is introduced into the system, it will bind into the repressor, and then the repressor can no longer bind to the promoter, which will then allow transcription to occur and the GFP to be expressed.
So when we were originally designing our biosensor, we had two main designs, the first being a linear system, which is shown on the top, and then the second being a dual promoter system shown on the bottom. And the major difference between these two systems is that the dual promoter system contains two promoters. The first is on the antisense strand, right here, and it controls PBRR, and the second is a forward promoter, right here, and it controls GFP. And the dual promoter system addressed a major problem that our linear biosensor had, and that is that as the GFP was expressed, the PBRR was also expressed, and that created more repressor protein, which was then able to bind back to the promoter and operator, stopping further transcription of the system. So then you would need more lead to bind to that newly created repressor so that RNA polymerase could read the system and further transcribe GFP. So in the dual promoter system, even though PBRR was still being expressed and the repressor was still being created, there were now two places where the repressor could possibly bind, either on the first promoter or the second promoter. And since the repressor equally spreads out between the two, there is now less repressor on the promoter controlling GFP. So this made this system a more sensitive biosensor. However, because of the two promoter sequences, it resulted in a palindromic sequence which causes the DNA to fold onto itself, making it very hard to synthesize, so we went with our linear system. Here is a plasmid map of our linear system. As you can see, there's the GFP gene, and two RBSs and a terminator. In between the RBSs, there's the promoter and operator sequence. We've also highlighted the two enzymes we used in our digestion, ECOR1 and XBA1.
So as you can see, this is a graph taken from a study that was conducted in Mumbai, India at the Central Institute of Fishery Education. And as you can see on the x-axis, we are measuring by PB2 concentration per micromolar, and on the y-axis, we are measuring by fluorescent intensity by gamma value. So as you can see, when we reach 250 Pb2 ion concentration, we reach the highest fluorescent intensity, which is at 200 gamma value. After, you see a major decrease in the fluorescent intensity due to the fact that the bacteria can no longer tolerate any more Pb2 ion concentration past 250 micromolar. Also in the same study, but not shown on the graph, the GFP is at its most intense at 12 hours.
Okay, so moving forward, we'd like to tweak our design of our biosensor a little bit by making it more sensitive and getting results faster. And after we do this, we'd like to put it on the market. That way people can test water in their homes, schools, and other companies to avoid crises like Flint from occurring again.
We also hope to adapt other genes in the PBRR system in Ralstonia mellodorans so that our biosensor can not only detect lead but also resist it, so we can turn contaminated water into clean, purified water. Thank you very much.
Hi everyone, I'm Emily. I'm Golda. I'm Elise. I'm Alice. I'm Erin. And we've created a nicotine biosensor. Nicotine is a harmful substance found in cigarettes and other equipment that's related to smoking.
The Surgeon General says that smoking is harmful and indoor environments are a good approach to prevent these harmful effects.
So even the government and other places recognize that there are two places in particular where secondhand smoking affects people more than usual. In a hospital where people have a lowered immune system, and in airplanes when you're in the same contaminated air for hours at a time. Also, people that are very susceptible to smoking are teenagers, and it's really dangerous because their parents don't know they can leave the house and just they don't know where they've been or what they've been doing. What's also really the problem with secondhand smoking is that people don't really understand how far-reaching the consequences are. And parents think, I'll take a few drags in the house, like how bad could it be? And the problem really is awareness. And even now, they've recently found out that owners of pets who smoke, their pets have a higher risk of getting cancer.
As Golda and Elise have said, the harmful effects of smoking, especially in these problem areas, are irrefutable. In response, we've created NicoSense, a biosensor that turns red in the presence of nicotine. We hope that this will be implemented as a strip to attach to walls and rooms. The host organism that we use for our biosensor is a strain of E. coli called DH5 alpha. It's frequently used by scientists because of its high competency and because it's harmless to humans. Additionally, the gene responsible for producing the red color in the E. coli is the RFP, or red fluorescent protein gene.
This is our sequence that we made. As my partner said before, there's 4 main parts in the sequence: the RBS, the promoter, the RBS, the open reading frame, and the terminator. As you can see, we begin with the promoter and then the repressor, which is very important in our biosensor, as it will not turn on the RFP gene until it detects nicotine. And then, as you can see in the pink, it's the first part of our oxidase gene, which is very important in our biosensor too, which Erin will explain later on. And on the second part, you can see that there's an overlap in the very beginning of the sequence. This is because we used a different method of putting together the DNA, which is called Takara cloning. And then the reason why we had to separate the sequence into 2 parts is because we had to keep our sequences under 2,000 base pairs. And so we which is why we have 2 parts. And as you keep moving on, you see another promoter, which is an inducible promoter, which is an on and off promoter, which we control. And so the RFP gene can be controlled by us.
So our group used Takara cloning instead of the normal ligation method because we couldn't fit the oxidase into one part of the sequence or the other. If we had used ligation instead of Takara, we would have risked losing base pairs by splitting the oxidase. But with Takara, you could just add the overlap between the 2 fragments, and during transcription, this would seam them together. So our biosensor works when nicotine is present. The repressor will bind to the nicotine inside the cell and allow the rest of the circuit to run. Also, we added an oxidase which degrades the nicotine inside the cell, and because the cell wants the equal concentrations of nicotine inside the cell and outside the cell, it'll continue to take in nicotine, and this will increase chances of the RFP being expressed.
So the cloning vector that we used is called PUC19, and the restriction enzyme that we chose is called SMAR1, and we used this one because it has blunt ends and doesn't cut into our sequence.
So I spoke earlier about how the main problem with secondhand smoke is awareness, that people don't realize the far-reaching consequences of just taking a drag near another person. In 2010, the number of teenagers smoking was 23%. Today, it's 9%. And if we keep on raising awareness of how nicotine pervades the environment, even to outside people that aren't smoking, we could finally be the generation that ends smoking. Thank you for listening, and again, questions are being answered at the end.
Are you guys ready? Okay. Hi, we're Team A. My name is Lana.
I'm Reggie.
My name is Zoe. My name is Alyssa. We created a biosensor called K-Smart. It detects potassium. So why did we choose to create a biosensor for potassium? All of us are athletes in one way or another, and that means that physical health and our diet is extremely important. I have a friend, and she had an extreme lack of potassium and salt in her system, and it caused her extremely painful muscle cramps to the point of sometimes she couldn't walk.
Potassium is needed in the body for muscle function, proper function of cells, tissues, and organs. It's an electrolyte, and it helps with heart activity. Lack of potassium can result in hyperkalemia, nausea, dizziness, and excessive sweating.
K-Smart is the potassium biosensor. We use a strand of E. coli called DH5 alpha to create this biosensor. When there is no potassium detected, the red fluorescent protein will glow, but when there is potassium detected, the bacteria will not glow a red color.
And so K-Smart was designed by using the iGEM catalog, which had a bunch of parts of DNA that we could use to detect our potassium. And so we used a potassium-sensitive operon, and we combined this with the RFP gene, or the red fluorescent protein gene. And as Lana said, when potassium was present, the RFP gene was not expressed. And then we combined the operon and the RFP gene on SnapGene, which is a program that allows you to combine different pieces of DNA. And then we also use that to create primers, which are pieces of DNA that help with replication. They anneal DNA and initialize the replication. And we also use SnapGene to look at the PUC19 vector and the restriction enzyme sites that were on it. And we compared these to the sites that were found on our insert. And then we copied 2 restriction enzyme sites, One of them is XBA1, and the other one is PST1, and we put these at the beginning and the end of our insert, so we could insert them into the PUC19 vector and create our insert.
K-Smart can detect potassium in bodily fluids such as blood, sweat, and urine, and it can detect potassium in water, foods, and other substances that has potassium.
And what's really exciting is that we actually, we found it literally this morning that you can see here in our colonies in the circle, those two slightly reddish colonies are actually two colonies that expressed our gene. So we were able to make a biosensor. Like we didn't have time to test it, but it's really exciting that we have colonies that express the gene. Thank you for watching.
Hey, good afternoon. We're Team C. I'm Ben.
I'm Andrew.
I'm Connor.
And I'm Micah, and today we'll be addressing the arsenic contamination issue. Arsenic is a naturally occurring poisonous element. It's found in wells, soil, and groundwater. People consume arsenic through contaminated water or foods irrigated with contaminated water. And symptoms consist of vomiting, diarrhea, abdominal pain, and sometimes cancer. And the affected areas are Bangladesh, Argentina, and Chile, some of the affected areas.
So now that we realize that arsenic contamination in water is a real issue, we need to create the gene that would detect this. So using the iGEM catalog, we found an arsenic-sensitive repressor so that when no arsenic is present, nothing happens with the circuit, but then when arsenic is present, the indicator gene, which is the GFP that you could see after, turns on. So, as we all we used restriction enzymes, which are basically molecular scissors, which will cut our DNA and the PUC19 plasmid into our complementary sequences, as you can see there, so that they can bond together through the process of ligation. And the ones that we used were XBA1 and EcoR1. So now what we need to do is clone to make a recombinant plasmid with our gene in it. So what we did is we used the restriction enzymes and cut our DNA, and we cut the PUC19 vector. So then through ligation, we were able to make the recombinant plasmid, and now it was ready for transformation.
Introducing the DH5 alpha E. coli cell. As Ben stated previously, this is a three-step process to make this final cells that we have right here on screen. So first we had to make the gene sequence, then we put the gene sequences into plasmids, which we subsequently put into these cells. So we plate these cells in order to test for gene expression afterwards. Introducing WASH, the final thing. Whoa. Alright. How WASH works. WASH basically acts as a detection agent. When placed into arsenic-contaminated water, the repressor genes on the gene sequence come off and attach to the arsenic ions in the water. This allows the rest of the gene to be expressed, which includes the GFP, thus allowing a visual indicator of a glowing green fluorescent cells in the water to show that arsenic is in fact contaminating the source.
So as Andrew said, the purpose of our product is not only to indicate that arsenic is present, but also to remove arsenic from solution so that we can create viable water for people to drink. And so our first idea was to use a centrifuge which will spin down the bacteria and allow for arsenic to settle at the bottom, which you can then remove. But we realized that this was relatively ineffective compared to distillation. The way that distillation works is you have a solution of arsenic-contaminated water, and you boil that. Once the water evaporates, it will then condense back down into water, liquid form, and that water will be completely pure and will have limited amounts of arsenic inside. Once we have distilled the water, You could then have to determine the pH in order to put back necessary nutrients that didn't evaporate, and also to allow for the pH to be similar to your body's pH. The way that you can do this is you can add baking soda, lemons, or even pH drops. And we'd like to acknowledge on behalf of the entire class, Con Edison, the New York Building Congress, and the Albert Merkin School of Engineering, as well as Professor Delagrammaticus, Professor Medvedik, as well as our TAs, Ed, Mike, Michael, Chris, and Keith, as well as Alex Newman.